Welcome to the Deep Dive. We're here to give you that knowledge shortcut, digging into the week's most interesting research. You know, when most people think about what could go wrong with an electric vehicle, their minds just stream. It jumps straight to one thing.
The battery.
Exactly, the massive high-voltage battery, that multi-thousand-dollar unit everyone is sort of fixated on. But today, we are diving into a really surprising truth that we pulled from our sources. The most common point of failure in an EV. It's not that big battery at all.
Not even close, really.
It's actually found in these smaller, almost invisible components that are operating under just unbelievable stress.
Exactly right. And that's our mission for this deep dive. We want you to shift your focus. The real story of EV reliability, it's a lot more complex and frankly, a bit more counterintuitive than just battery anxiety.
Okay, so we're not talking about range.
No, we're not worried about capacity today. We are going to unpack the delicate physics and the huge engineering challenges happening inside the car's power electronics. That's where the real fight for reliability is happening right now.
Okay, let's unpack that. Let's introduce the main culprit here, the component that, according to monitoring data, is behind the majority of these faults. It's called the DC-DC converter. And you should think of it as the vehicle's hidden power manager. It's just a silent little box tucked away somewhere you'll probably never see.
And its job is absolutely mission critical. I mean, it's operating constantly under incredibly high tension. The main battery, the big one, it runs at somewhere between, say, 400 and 800 volts.
Right, massive voltage.
Just huge. And you can't run your headlights or your stereo or your sensors on 800 volts. So the DC-DC converter's job is to take that immense power and step it all the way down to a stable 12 volts.
The classic 12-volt system. Why is that specific voltage still so critical in such a high-tech car?
Because that stable 12-volt supply is, well, it's the lifeblood for basically everything else in the car that isn't the main motor.
So all the auxiliary stuff.
All of it. We're talking about power steering, brake systems, window motors, the big infotainment screen, and this is the crucial part, all the electronic control units.
Yeah.
The ECUs.
The brains of the car.
The brains of the car. If that 12-volt supply fails, the car just shuts down. It doesn't matter how much charge is in the main battery.
And this is where it gets really fascinating. And this is based on data from over 240,000 EVs out on the road. This tiny unsung component is the single most frequent point of failure.
It is. The numbers are pretty stark.
I found this staggering. Faults that are specifically related to the DC-DC converter. They account for 38.20% of all reported faults in that huge data set.
38%.
Yeah. And to put that in perspective, compare it to the main power battery, the one everyone worries about. That's responsible for about 25.90% of failures.
So it's not even a close race.
Not at all. When you look at those numbers, it's the converter, not the battery. That's the real reliability choke point for engineers right now.
It completely flips the common narrative. It shows the biggest risks aren't in energy storage, but in the complexity of voltage management. And that little box is just so delicate because of the environment it has to survive in.
Okay, so let's talk about that environment. Why is it so delicate?
Well, you can break it down into two main pressures. First, you have just intense electrical stress.
Okay.
The converter is constantly getting hit with these high current peaks, potential overvoltages. Think about sudden demands when the motor restarts or when you turn on the AC.
So it's not a smooth flow.
Not at all. These events are like electrical bullets. They can cause severe damage to the sensitive components inside. It has to endure this constant turbulence.
So it's fighting to keep that 12V stable against all that turbulence.
Precisely. And that leads to the second pressure, which is the control system complexity. It needs an incredibly robust, intricate control system to constantly juggle that fluctuating high voltage input while meeting the shifting demands on the low voltage side.
It has to be perfect.
It has to be a perfectly precise 12V supply. If that control loop breaks down, the whole system just destabilizes almost instantly.
So when it fails, what actually happens? I mean, are we talking about a dead radio, or is the car completely bricked?
Oh, it's much more severe. Most DC converter faults are immediately classified as a level 2 serious fault.
And what does that mean in practice?
It means it directly and immediately impacts the car's performance. It often triggers the car to protect itself, like by severely limiting the power to the main drive motor.
Wow.
And the reports detail the specific failures. You see things like input or output overcurrent faults. But the really catastrophic one is an IGBT short circuit.
An IGBT.
It stands for insulated gate bipolar transistor. It's a core switching component inside the converter. When that shorts out, the whole conversion process just stops, dead.
Well, hold on. So the main traction battery could be sitting there at 90%, ready to go for another 200 miles.
Fully charged.
But because one tiny transistor fails inside a component the size of a book, you're stranded. That feels like a huge design vulnerability.
That is the exact engineering challenge. The car stops because its brains, the ECUs, are starved of their 12V power,
Right.
which brings us right to the physics of why these things fail.
Right. We have to talk about overheating.
Yeah.
But the source material makes this really crucial distinction that I think changes everything.
Mm-hmm.
Can you explain why we need to stop thinking about just heat and start thinking about temperature?
Yes, this is a nuance that thermal engineers are obsessed with, and for good reason. We have to distinguish between heat, which is a measure of total energy, and temperature, which is the intensity of that energy.
Okay.
One of the papers used this brilliant analogy. It said, there is more heat in an iceberg at -4 degrees Celsius than there is in my cup of coffee at 60 degrees Celsius.
That's a great analogy. So the iceberg has way more total energy, but its temperature is obviously very low. Why does that difference matter for a tiny silicon chip?
Because a chip only cares about the intensity. It only cares about temperature. For the delicate silicon inside, high temperature is the enemy because it literally alters the physical properties of the material.
It changes the silicon itself.
It does. A rise in temperature decreases the material's band gap.
And the band gap is what exactly?
It's a fundamental property that's essential for controlling the flow of electricity. It allows for that precise, high-speed switching. So when a high temperature degrades the band gap, the component loses switching efficiency. It gets sluggish.
And a sluggish component probably wastes more energy.
Exactly. It generates more waste heat, and that leads directly to this really dangerous positive feedback loop of thermal failure.
Okay, so let's walk through that loop. How does it kill the component?
Right. So step 1, temperature goes up and the efficiency drops.
Okay.
Step 2, lower efficiency means more power is lost as waste heat inside the component.
Which I assume makes the temperature go up even more.
Precisely. That new heat raises the temperature further, which reduces efficiency even more, and the cycle just repeats faster and faster until you get a catastrophic thermal runaway and the whole thing just breaks down.
And what makes this even worse? What are the silent killers that trap all this destructive heat right where it's being generated?
The silent killers are the materials we use every day for housings and support. Things like plastic coatings, epoxy, and especially air caps.
Air gaps.
Yes, they're terrible thermal conductors. In fact, they're fantastic thermal insulators. Air has a thermal conductivity value of just 0.02 WMK. It's basically nothing.
So a tiny gap of air between a hot chip and a cooling plate acts like a blanket.
A thermal blanket, exactly. It actively traps the heat and pushes that feedback loop towards failure. The whole engineering solution becomes a war on insulation.
So if the problem is this mix of complexity and brutal physics, how are engineers fighting back? Let's start with the design philosophy.
Simplicity.
Simplicity. The sources really drive this home. The complexity is the enemy of reliability. There was a great little case study in there about an engineer designing heated gloves.
Right. He chose this really impressive complex DC converter, a buck boost converter.
Super high tech.
Technically, yes, but the board kept overheating. The solution was to just be simpler.
They ditched the fancy converter for a basic circuit using pulse width modulation, or PWM.
That's right. PWM is just a simple way of rapidly switching the power on and off. It's much simpler, generates less heat, and has fewer parts that can fail.
It reminds me of that fantastic quote from the sources. In any design, the smallest, cheapest, and most reliable components are the ones you don't fit, because you don't need them.
That sums it up perfectly.
But, in a modern EV, you can't avoid complexity entirely. So what's the backup plan? How do they make sure the complex parts they do need can actually survive?
That's where qualification comes in. If you can't make it simple, you have to make it brutal. Engineers rely on a standard called AEC Q100.
The Automotive Electronics Council.
Right. It's a standard designed to guarantee the lifespan of these electronics before a car ever hits the road. And it pushes these components to the absolute breaking point limit.
How extreme are we talking?
Well, to get the highest rating, grade 0, a component has to operate flawlessly from a frigid -40 degrees Celsius all the way up to a blistering plus 150 degrees Celsius.
That is a massive temperature swing.
It's a 190-degree swing. And they have to prove they can survive that for years. The tests are designed to accelerate a lifetime of wear and tear.
They sound intense.
They are. You have things like high temperature operating life, or HTOL. The chip runs at its maximum temperature for 1,000 hours straight.
1,000 hours. Wow.
And then there's temperature cycling, which is maybe even worse. It subjects the component to 1,000 rapid swings between, say, minus 55°C and plus 150°C over and over again. That specifically tests for mechanical fatigue, the material literally being ripped apart by thermal expansion and contraction.
And at the same time, they're fighting that war against the silent killers you mentioned, the insulators.
Yes. The whole strategy is to eliminate those thermal bottlenecks. So they're getting rid of air gaps, replacing insulating plastics with these new advanced thermally conductive composites.
Some materials.
In a sense, yes. They conduct heat very well, but they remain electrically isolating so you don't short out the system. And this approach, it transforms the heat transfer from a simple 1D path like a chip to a heat sink into a much more effective 3D heat dissipation.
It pulls heat away in all directions.
Pulls heat away from the hot spots in every direction, which dramatically lowers the operating temperature and keeps that sensitive silicon stable for the long haul.
That is a phenomenal deep dive. The real battle for EV reliability, it's pretty clear it's being won or lost, not in the battery, but in this unseen world. It's about managing temperature, embracing simplicity, and just fortifying these tiny critical components against the brutal reality of the road.
Absolutely. True reliability comes from a holistic approach. It's that brutal pre-market qualification, the stress of AEC-Q 100, combined with smart thermal management to get rid of those bottlenecks. It's design and testing together.
So, what does this all mean for you? As our cars become these incredibly sophisticated computers on wheels, here's a final thought to leave you with. What other boring components are quietly waiting in the wings? Maybe a sensor, a small pump, a wiring harness, to become the next critical point of failure that absolutely no one is talking about yet. Thank you so much for joining us on this deep dive into the physics of failure. We hope you feel thoroughly well informed, and we invite you to follow the channel for more explorations into complex topics.